Question 19 gives us a displayed formula just for a change, and asks us first of all just to name that compound and write down its molecular formula. So the name, got a chain of 4 carbons, so it's bute. It's not got any carbon-carbon double bonds, so it's a saturated chain, so we put an in there. And it's got the OH group at carbon 2, starting to number at that end to keep the number as low as possible, so it's butan 2-ol is the name for that compound. The molecular formula, if it didn't have the oxygen, you count the carbons and say, right, there are 4. If it didn't have the oxygens, you just go, right, 2n plus 2 gives you 10, so that would be butane. And you can see that the only difference between that and butane is that you've added in the extra oxygen between the carbon and the hydrogen there. So it's still got 10 hydrogens, but it has an oxygen there. Whenever they ask questions like that, the way people very commonly lose marks is by writing that. But remember, a molecular formula is just a list of how many carbons, how many hydrogens, how many oxygens. So there's no justification for separating that hydrogen out from these other ones in a molecular formula, so that will get marked wrong. Okay, so that is the molecular formula. Okay, so then it wants to know about dehydration. And dehydration, remember, is an elimination reaction where you take away the OH group and you take away a hydrogen from a next door carbon, so that would be either this one or this one. And the conditions for that are concentrated sulfuric acid and heat. Okay, so those are the dehydration conditions. So 3 possible alkenes. Well, as I've already said, the reason you get more than one is in part the fact that you get 2 possible carbons which could lose the hydrogen if this one loses the OH, because it's got to be a next door carbon so you can get the double bond in between, but that means it could be either this one or this one. So let's draw the structures for those. Now it just says draw the structure, it doesn't say draw the structure in the same format, so you can if you want, but hopefully you're getting the message by now that it just takes too long to draw displayed formulae unless you have to. So I would be strongly tempted to just think, right, butan 2-ol is much more straightforwardly represented like that, and that means when you dehydrate it, you're going to lose the OH, you're going to lose a hydrogen from here or there, and that means you'll get a double bond either there or there. So that gives you straight away 2 products, that one or that one. But it says what are the 3 possible products? So again, what you have to remember is about EZ, that when you do this elimination reaction and form the double bond here, you're going to lock in the stereochemistry of the chain, because you're going to cut out the possibility for rotation. But before the dehydration, there's lots of flexibility there. So if you like, although we draw the chain like that because it's kind of neater, remember you can rotate around this bond all the time. So the chain won't always be organised like that. It could be organised like this. And of course, if you dehydrate with the chain organised like that, you're going to get a different isomer. So always when you're making alkenes, you have to consider the possibility, are there EZ isomers that you could make? Because in general you'd expect to get a mixture of both if they exist. For this one, but1ene though, there is no EZ isomer, because at this end of the double bond this carbon has 2 hydrogens attached. And if you have 2 groups the same at the end of a double bond, you can't get EZ isomers. So that one is unique as a but1ene. But here, but2ene, you can see you do have that situation, because this carbon has a methyl and a hydrogen. This carbon also has a methyl and a hydrogen. So they each have 2 different groups. That means you can get EZ isomers. And as we said before, the way you draw an EZ isomer is you keep one end of the molecule the same. So we're drawing that the same as that. And then the other end of the double bond, instead of going up on the opposite side from that methyl group, it's going to come down on the same side as the methyl group, and so you're going to get that. And those are the 3 possible alkenes. So then in part E, we have to compare the boiling points of compound A, which is that, and 2-methylbutane, which is that. So you can see the very similar looking molecules. The difference is that you have a methyl group here instead of a OH group there. So hopefully you're well practiced with this now. The answer is that this one, compound A, will have the higher boiling point because it can form hydrogen bonds. Okay, remember, anything with an OH group in there can do that. So it can form hydrogen bonds, whereas, it's always got to be a whereas, there's always got to be a comparison. 2-methylbutane, which is this, and rather than just say it can't, say what it can do. So 2-methylbutane can only form induced dipole-dipole forces. Still not enough, because they'll say, yeah, okay, who cares? So you say hydrogen bonds are stronger. You have to spell that out. Hydrogen bonds are stronger than other intermolecular forces. Okay, make sure it's a clear comparison. So it takes more energy to break them. And now we've got there. Part F, it wants an equation for incomplete combustion of this compound to form carbon monoxide. Combustion reactions are one of those cases where you don't need to draw the structure out. Remember, most equations in organic chemistry you must show the structures, but because the structure's all destroyed in combustion, you don't need to. So you can either just write the molecular formula, which we already worked out earlier on, is C4H10O, or you could write C4H9OH or whatever. But that's your compound A, and it's going to react with some O2s, and we'll work out how many in a minute. So we leave a space there. And it's going to give you 4 carbon monoxides rather than carbon dioxides this time, because it's what it specified for incomplete combustion. So 4 of those, because there are 4 carbons. 10 hydrogens means 5 waters, because 5 lots of 2 gives you the 10 hydrogens. So if we add up the oxygens on the right, we've got 4 there plus 5 makes 9. So there must be 9 altogether on the left. One of them is already there. Make sure you don't forget that one. So out of the 9, that one is already there, so we just need 8 more. So that's 4O2. And that's your answer. In question 20, we first of all have to give a name to this alkene. So we find the longest continuous chain, which is going to be 1, 2, 3, 4, 5 bonds like that. So 1, 2, 3, 4, 5, 6 carbons altogether. So that gives us hex as the root of the name. And it's not going to be an because it's an alkene, it's unsaturated. So it's going to be ene, and I've left the gap because we need a number to specify where the double bond comes. And there's nothing else, there's no alcohol group or aldehyde or whatever, so the ending is just going to be ene, like that. Got to decide which end to start numbering from, so we want to keep the number as small as possible, which means we're going to number like this. Okay, and so the double bond is between 2 and 3, but you quote the lower number, so it's hex 2-ene. And the only thing that's not included in that then is this methyl group here, which you can see is attached to carbon 2, so it's 2-methyl hex 2-ene. And then in part B, it asks us to explain why this compound doesn't exist as a pair of stereoisomers. So that's asking about EZ. Stereoisomers in the context of alkenes, remember, means EZ isomers. And the requirement for that is that you have to have 2 different groups attached to each of the carbons of the double bond. And you can see that's true for carbon 3, because hydrogen is different from propyl, but it's not true for carbon 2, because it's got 2 methyl groups attached. So what you need to spell out is that one of the carbons in the alkene group has two identical groups attached. Okay, you really have to spell this out, and I would just spell that out, 2 lots of CH3, so that everybody knows what you're talking about, which means that EZ isomers can't exist. Because EZ isomers can only exist if the consequence of rotation around the double bond was to produce two different compounds. But you can see if you did rotate around that double bond, you'd just swap those two methyl groups over and it would still look exactly the same. Part C wants to know how we could make compound W. That's the same thing, just drawn out there as a skeletal formula, and it wants to know how we could make it from an alcohol by dehydration using those conditions. So we've just got to choose an alcohol, and you can see that we have a choice of two because we just need to have a hydrogen at one end of this double bond and an OH at the other, and if we eliminate those two to form a water, we'll get the double bond in between. So we have the choice of putting the OH either there or there, and that will give us two different alcohols. So either one of those would be fine. So you could have either this or you could have that. Okay, and either of those would work. Neither of them would give you only that one, because if you eliminate the OH from this carbon, you might eliminate the hydrogen from there, which is what you want to do, but you might eliminate it from here or here. If you eliminate it from this one, again, you might eliminate it across there, but you might eliminate it across there. So neither one is perfect, but either one is fine as an answer. And then it wants an equation for polymerization of alkene W. The thing with polymerization is that you can do it with skeletal formulae if you get used to doing that. But it's one of those cases where it's probably easier to go back to this kind of representation, because this is the way we sort of learnt to do it, and it's very easy to then slot any alkene into this general recipe. So if we represent compound W using this kind of arrangement, we've got the two methyl groups at this end, and then at this end we have a propyl group, CH2, CH2, CH3, and a hydrogen. The advantage of drawing it like that is that it's then very easy to draw the repeat unit of the polymer, because the repeat unit of the polymer is, for any alkene, is arranged like that. So the same two carbons across the middle, and whatever's on the end of these four bonds is still there at the ends of those bonds in the repeat unit. So you have CH3, CH2, CH2, CH3, CH3, and hydrogen. So that's the monomer, that's the repeat unit, but what it actually asks for is an equation, and in the equation, remember, we use N to represent a big number. So whatever that big number is of alkene molecules, they combine together to give you this repeat unit, linked together by these linking covalent bonds. So you draw these square brackets around it, and remember the brackets must slice right through the middle of these linking covalent bonds when you draw it, and that's going to be repeated N times. So you put the N down there, and that's it. It's an addition reaction, so there's no other product. That's your equation. Part E, it wants two possible products when compound W, which is this, reacts with H2O. So remember, these alkene reactions are always electrophilic additions. So we've got water adding across the double bond like that. So H goes on to one end, OH goes on to the other. But the complication is that it could go the other way round. So you could have OH at this end and hydrogen at that end. So that's why you have two possible products. So we can easily then draw what they would be. So if it adds the top way round, we're just going to, of course, lose the double bond. It just becomes a single bond now, but we get the OH here, and then there's the propyl group. If it adds the bottom way round, then the OH is going to go on here. And we're going to get that. So those are the two possible products. And then in part F, it asks us to give those names. So this one, you've got longest chain 1, 2, 3, 4, 5, 6. Of course, that hasn't changed. So it's hex, but now it's an rather than ene because the double bond is gone. So it's hexan. We're going to number it to keep the number of the OH as small as possible. So we're going to number it because that's going to be the ending, right? So it's going to be ol at the end there. So we're going to number it 1, 2, 3, 4, 5, 6. So it's hexan 3-ol is the root of the name. And then carbon 2 has got a methyl group attached. So it's 2-methyl hexan 3-ol is the way to number that one. This one, again, is hexan ol is the root of the name because you've still got that chain of 6 across there. But now, numbering from this end, the OH is on carbon 2, so it's hexan 2-ol. But of course the methyl is still on 2 as well, so it's 2-methyl hexan 2-ol. So next it wants the conditions for that reaction. And remember, it's not an easy reaction to get to work because the bonds in water are very strong, so it's quite difficult to get that to happen. So you can't just use water, you have to use steam, and you need a catalyst, specifically phosphoric acid. Okay, so those are the conditions that you need to learn for adding H2O to an alkene. And then it wants a word for the role of H2O, and that word, remember, is electrophile. And that relates to the mechanism, because when the water attacks the alkene group, what happens is that it accepts a pair of electrons from the alkene group, and an electron pair acceptor is an electrophile. So electrophile is the word you want, and the explanation you just have to say is that water acts as an electron pair acceptor. If you're not sure about what that means, we can just briefly recap on that mechanism. But you don't need that in your answer. That's absolutely all you need, that, but it may just be worth reminding you what happens here. Actually, the mechanism you need to know is with HBr or HCl rather than with HOH. The catalyst makes it slightly more complicated. Okay, so when the water attacks the alkene, it's going to attack this way round, because remember the delta positive end, which is one of the hydrogens, is going to be attracted to the high electron density of the pi bond there, and that makes this happen. Okay, so the electron pair from the pi bond is used to form a bond to the hydrogen, and this bond breaks, forming a lone pair on the oxygen. So that gives you an intermediate, which is going to look like this. Okay, double bond is now a single bond, and we'll either have a positive charge at this end if the hydrogen goes on there, or we'll have a positive charge at this end if the hydrogen goes on there. Right, because the hydrogen can only attach to one or other of those carbons, and whichever one loses out is going to end up short of electrons, so we'll have a positive. So I've drawn the same thing twice there. So the positive charge will be there if the hydrogen adds to that end. So we have these alternative carbocation intermediates formed, and the OH will become OH minus. In reality, it's not quite as simple as that because the catalyst gets involved here, but let's just ignore that for the sake of simplicity here. And then in the second stage, that OH minus ion will attack the positively charged carbon like that. Okay, so curly arrow going from the lone pair directly to the positively charged carbon like that, and that gives you your alternative products. So if it goes via this top intermediate, you'll get OH attached there, and if it goes via the bottom one, you'll get OH attached there. So that's why it's called an electrophile, because of what's happening in that first step, that it's accepting this pair of electrons that comes from the pi bond and attacks the water there. So this then has actually given us all the information we need to answer part I, which is really just to explain which of these two will be formed in the greater amount, which one is the major product. And that, remember, is determined not by how stable the products are, but how stable these carbocation intermediates are. Because the more stable the carbocation intermediate, the more easily it will be formed, and so the more of it will be formed, and therefore the more of the product it leads to will be formed. So if you compare the two, this one is a tertiary carbocation, because the carbon with the positive charge has 3 other carbons attached. This one is a secondary carbocation, because the positively charged carbon has only 2 other carbons attached. And the rule, remember, is that tertiary are the most stable, then secondary, then primary. So what we're going to say is that this is the more stable carbocation, and therefore it will be formed more easily and will lead to the major product, which will therefore be this one. So to answer the question, we don't have to write out the whole mechanism or anything. We've already done that, but remember, that wasn't a required answer. That was just to make sure you remembered the story. But you need to make it clear which is the major product. So this one is the major product. And then your explanation is that it is formed via, and that's the key word. Okay, it's not that it itself is more stable, it is formed via a tertiary carbocation, which is this one, which is more stable and so more easily formed than the alternative secondary one. And it's important you give that detail in there. Say what both of the possible carbocations would be, and then give a clear comparison of which one is more stable. So more easily formed than the alternative secondary carbocation. Okay, so that sort of wording and those Markovnikov questions, it's really important to practice. Question 21 in part A is asking us to write down the structures of 4 different compounds which all share that molecular formula and which are all primary alcohols, meaning that the carbon with the OH is at the end of a chain, so it has only one other carbon attached. So when you get questions like that, the thing to do is to try to be systematic. So what I would do is start with the simplest case, which is if you've got 5 carbons, the simplest thing would be to say, right, let's suppose they're all in a chain. So we've got a chain of 1, 2, 3, 4, 5 carbons, and we'll put the OH on the end. So that would be pentan-1-ol. Obviously, if you put the OH on that end, that would just be the same thing drawn the other way around. So there's only one possibility that's a primary alcohol if it has a straight chain. So then you say, right, suppose it's not a straight chain. Suppose it only has 4 carbons in the main chain. And then you put a branch on it. And you can see there's only one way we can put a branch on that, because if we put it either there or there, it's the same thing. So let's put it here. And then we'll say, right, where can we add an OH group onto that will make a primary alcohol? Well, one thing we can do is put it there, because that carbon has only one other carbon attached, so that would be a primary alcohol, so that's one. And then the other two places where we could add an OH onto that skeleton would be either here or here. But again, you can see that it doesn't matter whether you put it there or there, it'll be the same thing, because remember, you can rotate around that bond, so those two positions are constantly changing places anyway. So whether you put an OH there or there, it's the same compound. So let's just put it here and say, right, that's our third possibility. So there was only one possibility if we had a chain of 5, 2 possibilities if we have a chain of 4 with 1 branch. So the other one must have a chain of 3 with 2 branches, which would be this. There's only one way to do that. And if we look at where we can put the OH on the end of a chain here, it could go here or here or here or here to make a primary alcohol. But you can see from the symmetry that all 4 of those are the same. So the product will just be that. And those are your 4 alcohols. So then in part B, it wants to know what's the product that could be formed if we dehydrate each of those alcohols. In other words, eliminate the OH and a hydrogen from the carbon next to it to form water. So in this case, if we take OH away from this carbon, we'd have to take the hydrogen away from that carbon, and that would give us this product. Okay, so that's where the OH was, that's where the hydrogen was that have gone to form the water, so you get but-1-ene. If we do this one, we'll lose the OH from here and a hydrogen from there, and that will give us this product. If we do this one, we'll lose an OH from here and a hydrogen from there, so we just have to check, is there a hydrogen there that we can remove? But yes, there is, because that carbon has 3 other carbons attached, so it must have a hydrogen as well, so that's fine, we can do that, and that will give us this compound. And finally for this one, if we eliminated water from here, we'd have to take OH from this carbon and a hydrogen from that one, but this is the one that won't work, because that carbon has no hydrogen, so it can't lose it to form water, and therefore it can't react, so that one has no reaction. That's it.